2.2 Subsets. So subsets. Set A is a subset of set B, symbolized A like a little weird C with a line underneath B, if and only if all elements in set A are also elements of set B. The symbol, A with that little C, it's saying A is a subset of B. If I have a line through it, it means set A is not a subset of set B. So to show that set A is not a subset, one must find at least one element of set A that is not in an element of set B. So what does that all mean? So determine the subsets, determine whether set A is a subset of set B. So what it's asking is everything in A inside of B? Is everything in A also inside B? So let's try. So boat, awesome, that okay. Train, plane. So everything in A is inside of B. That means A is a subset of B. So all elements of set A are in set B. That's all it is. So whatever set they're listing first, if everything in there is in the second listed set, you're good to go. Proper subset. Set A is a proper subset of set B, symbolized A with just the C no line underneath. B, if and only if all the elements of set A are also elements of set B, but they're not equal. So it's a proper subset if they're not equal. So let's see if these are equal. They're definitely not equal. So we can see if they're proper. So what it's asking is everything in A inside B. Is everything in A inside B? So jazz, pop, hip hop. Everything in A is inside B. So we would say A is a proper subset of B. And why? So all elements of A are in B, and they are not equal. So that makes it proper. Alright, let's determine whether set A is a proper subset of B. So we have A, B, C, D, and A, C, B, E. Nope, that can't be proper, because they're identical. So set A and B are identical. So that means A is not a proper subset of B. Would it be a subset? Absolutely, just not proper, because they're equal. Number of distinct subsets. The number of distinct subsets of a finite set is 2 to the power of n, where n is the number of elements in set A. So number of distinct proper subsets. The number of distinct proper subsets of a finite set is 2 to the power of n minus 1, where n is the number of elements in A. So if you want to find how many subsets it has, we can use 2 to the power of n. If you want to find how many proper subsets it has, you can find it by using 2 to the power of n minus 1. So example 3. Number of distinct subsets. So we're talking about here, distinct subsets. Determine the number of distinct subsets for the given SLED. Then we're going to list all the distinct subsets for SLED. So for SLED, we have 4 elements. So since we have 4 elements, and it's asking for distinct subsets, we're going to use 2 to the power of n. And n is how many elements you have. So we have 2 to the power of 4. And remember, that's 2 times 2 times 2 times 2, which is 16. So of SLED, there are 16 subsets of SLED. I am not going to write them, I'm going to show you. We'd be here for a hot minute if I had to write that all. That's coming up soon, or not soon, at the end of the semester. Alright, so we have 16 different variations. So the first variation is exactly what you have, SLED. Then we have SLE, SLD, SED, LED. So that's all the triplets. Now we move on to doubles. SL, SE, SD. Then we have ED, LE, LD. Those are all our doubles. Now we just have singles. S, L, E, D. And you always have an empty set. An empty set is always a subset. So at the end, always put an empty set. So what you're doing here to list the distinct subsets is that you're just putting all the letters together. So we're doing SLE, SLD, SED. Okay, now we do LED, SL, just like that. Alright, this one also I'm just going to walk you through it. So element or subset. So part A is asking, is 3 an element of 3, 4, 5? The number 3 is in 3, 4, 5, so it's true. 3 is an element of the set. Part B, is set 3 an element of set 3, 4, 5? Because that little braces, the squigglies, say set. And that's false because this squiggly 3 is a set. And set 3 is not an element of set 3, 4, 5. So yeah, 3 is in there, but that's not saying, that's not the set. Here we have set 3, and here we have set 3, 4, 5, so they're different. Part C, is set 3 an element of set 3, set 4, set 5? That is true, because set 3 is in the set as a set. So what this is saying, this second part here, it's weird, is that we have a set of sets. So we have set 3, set 4, set 5, and set 3 is in there. All right, part D. Is set 3 a proper subset, or excuse me, a subset of 3, 4, 5? So part D. Is 3 a subset of 3, 4, 5? That's true because every element in the first set is in the second one. So set 3, it's in there. Yep. Is number 3 a subset of set 3, 4, 5? No, it's not, because 3 is not in braces. Therefore, this little thing right there, that means therefore. It's not a set. So in order to be proper or regular subset, you have to compare 2 or more sets. F, is an empty set a subset of 3, 4, 5? That is true because every set is a subset of an empty set. So empty set is a subset of every set. I said that backwards. All right. Let's go back to our notes. All right. Malik is going to purchase ice cream. To their ice cream, they can add any of the following toppings: hot fudge, whipped cream, cherries, butterscotch topping, caramel topping, nuts, Reese's Pieces, M&Ms, gummy bears, and rainbow sprinkles. How many different variations of ice cream and toppings are possible? So we're talking about how many different variations. That means how many distinct subsets. So we're going to be using the formula 2 to the power of n. So we need to know how many elements do we have in here? How many toppings do we have? So let's count. We have hot fudge, which is 1, whipped cream, that's 2, cherries is 3, butterscotch is 4, caramel is 5, nuts is 6, Reese's Pieces is 7, M&M's is 8, gummy bears are 9, rainbow sprinkles 10. So that means we have 10 toppings. So we're going to plug it into our formula. We have 2 to the power of 10. So remember, that's 2 times 2 times 2 times 2 times 2, 10 times, or just use your calculator. So we get 1,024 different variations. So if you go into this ice cream shop and this is what they have, and that's pretty standard for an ice cream shop or like a Froyo place, Usually you get about 10 toppings. You can go there 1,024 times and have it be different every single time. Life goals, right? Fun fact about Reese's Pieces, you can stop now if you don't care. So Reese's Pieces, they were going under. They weren't, like, people weren't buying them. I love Reese's Pieces. So people weren't buying them. They were about to, like, stop making them. So E.T., right, the movie E.T. from Steven Spielberg, when they were making the movie, so when you make movies, you seek out advertisements. So, like, if you ever see, like, a Coke or a Pepsi inside of a movie, it's because the company is paying to be in that movie. So Steven Spielberg went to M&M's and said, "Hey, we want you to be in the movie," but M&M's said no. So Steven Spielberg was like, "Fine, we'll go to the next thing." And at the time, everyone was trying to compare Reese's Pieces to M&M's, and I'm sorry, you can't. It's two very different things. So they went to Reese's Pieces like, "Hey, we want you to be in our movie." And that's what saved Reese's Pieces, was because they were in that movie. They were in E.T. If you haven't seen it, look up that scene. Just look up, like, Reese's Pieces E.T., and you'll see what I'm talking about. Anyways, random fun fact. Now you know.